Our next speaker of the session is Sudipta, and he'll be telling about area theorem in black holes.
Okay, so great to be here at this amazing time, and thanks, Paddy, for being at age 60 so that we can come here and join this. Okay. So what I'm going to talk about, some work which is a bit older work. I'm not going to talk about because I know that Paddy will enjoy this work. That's why it is being chosen. But it's a pure general relativity and extension of general relativity result, and these are my collaborators, which mostly I have worked with them. So let's start with the idea of black hole entropy, and this is Bekenstein, who last year passed away. The idea of black hole entropy is a brainchild of Bekenstein. His great idea that what happens if I throw a coffee cup into black hole. I think I should talk about also Wigner. So the idea that you can use black holes to violate the thermodynamics second law outside universe leads to the consideration that you must ascribe a concept of entropy with the black hole itself. And it turns out that entropy is proportional to the area of the horizon. This is a classic result, and it is well motivated because we all know black holes have event horizon. They hide information from us. So it's quite natural to associate the entropy. What is not natural is that entropy being proportional to the area of cross section of the event horizon, which is quite unusual for a thermodynamic object, for entropy not being proportional to the volume, that being proportional to the area. This area proportionality of entropy is a good news because in classical general relativity, what we have is called the famous Hawking's area theorem, which says that area of the event horizon of the black hole cannot decrease as long as you are not doing something weird like negative energies or violating, say, cosmic censorship. The area of the event horizon cannot decrease. And the basic proof of area theorem based on this famous equation by Rai-Chaudhuri, which dictates how the expansion and shear of the event horizon changes as the matter goes into the black hole. So this equation is entirely geometric. If you use Einstein's equation, then this RAB Ka Kb is substituted by TAB Ka Kb. Then you use null energy condition saying that the TAB Ka Kb, this object is a positive definite, and then you can show that d theta d lambda, the change of expansion of the area, is negative definite. You also assume that finally the expansion of the black hole settles down to 0. So this is exactly like an analogy with thermodynamics. You have a fluid, you put some perturbation to it, the fluid changes, it has expansion and whatnot, but you assume that the final state, the fluid goes to equilibrium. That means the expansion, everything goes to 0. And you can make it more formal by appealing to the statements of cosmic censorship, null completeness, but at the end of the day, this is what it means. And both together tells you the expansion of the event horizon must be positive. Expansion being the change in area, which says that area of the event horizon must be increasing. Of course, there are technical assumptions behind these proofs, which I am not going to show you. It's not much necessary. You can write down, for example, a bit redundant, but it will be useful later, part of linearized version of this second law. So think of this as a direction of time where lambda is some time on the event horizon being a null surface. You have to be a bit careful of what the coordinates you use. So if you have not thrown anything into the event horizon, think of this line, the length of this line represents the area of the event horizon. And then the area would have remained the same. It's like a static or stationary black hole, like a short shell black hole. Nothing is happening. The area of the event horizon is always same. So this would have been the unpart of event horizon if matter have not fallen into it. But if you throw matter into it, the event horizon will start expanding. It has some teleological properties. It will start expanding even before the matter has entered into the event horizon. And then ultimately it will settle down into a final stationary state. The area of this state is larger than the area of this state. And you can show that if your perturbations are small, then you can ignore all theta square and sigma square term. And again, you have a version of the second law. Okay. You have to assume that the final state of the event horizon, it is stationary. And you know the studies of quasi-normal modes and so many things indeed shows that black hole stabilizes. It's a stable system. The quasi-normal modes have right sign so that the perturbation die down. Apart from there are some crazy places where it doesn't happen. Now, this area theorem is fundamental is the basis of black hole thermodynamics. because area theorem tells you there is a second law, and then on the basis of that you have the first laws, and then you have the quantum field theory in curved spacetime, which leads to the black hole temperature. So the centrality of black hole thermodynamics is based on this area theorem. Now, of course, the area theorem is explicitly dependent on Einstein's equation. So if Einstein's equations are not true, area theorem is not true. Let's go back and ask that what if general relativity is not the fundamental theorem? What if there are corrections to general relativity which has been pursued in many various areas, and there are many motivations. One of the fundamental motivation being that is a non-renormalizable theory, at least perturbatively, and we believe there will be higher dimensional operator in the language of quantum field theory, and they will correct, and some higher length scale you will see these operators. And therefore, you believe the generic effective Lagrangian of gravity should be written into this form where there are these higher curvature correction terms. And it could be any term, okay, consistent with diffeomorphism invariant should come, if you think from a quantum field theory point of view. Note that once this higher curvature terms comes, there will be new dimension full constants. That is very important. Of course, if you are doing quantum field theory, all this should be determined by one length scale, the Planck length scale. But you can think of phenomenologically, there will be new dimension full constant. And in then, the relations between mass and horizon radius, there could be various possibilities. And you can think of various formulas for the entropy once there are new dimension full constants in your theory. The dimensional argument can give you new things. And therefore, the black hole entropy need not be proportional to the area. So if you add higher curvature corrections to the black hole entropy action of the theory, you may have different expression for black hole entropy. And this is well known. This has been first discussed by Wald and then Wald and IR, and then after that so many people, that if you have a diffeomorphism invariant Lagrangian, you have a complicated expression for black hole entropy which will obey the first law. So this comes from by deriving the first law, what is called the stationary version of first law, which are Wald and Iyer, and they could identify an expression where you take your Lagrangian. This Lagrangian is a function of metric and the curvature and maybe the derivatives of the metric. Let's ignore the derivative part. You functionally differentiate with respect to the curvature. You get some object x, and you integrate. These are the binormals on the horizon cross section. Integrate over this d minus 2 dimensional cross section. You get an object. You call that object, multiply by 2 pi and everything to get these factors correct. So that's not important. You get an object which will obey the first law. And indeed, if you do use Einstein-Hilbert Lagrangian, you have to believe me, indeed goes back to area by 4. So in general, entropy is not proportional to the area beyond general relativity. This Wald formalism is derived long ago and is being, beaten to death. So then the question comes, okay, my entropy has changed, my field equation has changed, how do I derive a second law? And of course, this is not just an academic question, because many, okay, there is no experimental observation, but it's a bit serious than that. Many of the theories predicts that there will be higher curvature corrections, and many of the higher curvature corrections have explicit black hole solution. So you remember the old argument by Bekenstein that there will be a possibility of violating second law in the outside universe in the presence of black hole still applies. So you need some version of second law once the theory has changed. So we want to save the second law in a world outside a black hole of a theory with higher curvature terms. One must seek an appropriate generalization of the Hawking's area theorem. So your fundamental assumptions are same, that the matter field obeys null energy condition. You also assume a bit, it's a courageous assumption. You assume that the cosmic censorship also holds true in these theories, and you also believe that there are nice black hole solutions. And then you want that there will be a candidate entropy, and I want this entropy to obey an increased theorem as in case of general relativity, using my new field equations. Not only that, you can ask more interesting question, what are the nice properties of GR? For example, positive energy theorem, does it hold with these higher curvature terms? Generic higher, what kind of higher curvature terms? Which will more interesting question will be violate the positive energy theorem. You can have a system, solution whose area mass is negative compared to the area mass of the Minkowski space. So that will be interesting questions. All these have been pursued. So let me, before going into the calculation and showing what happens, let me fix my notations. You give me a Lagrangian of L, I'll calculate this quantity, differentiate this Lagrangian, integrate over the cross section of the event horizon. I call this object to be a world entropy. It's just a name. For stationary black hole, this entropy will obey first law, the stationary version of first law. So I'll denote it by SW. Now, while deriving this world entropy, if you follow the World's paper, there will be a lot of ambiguities because it comes from a necessary and no other charge construction. Even in field theory, no other charge construction has ambiguities. Because of that, what you can write down a general black hole entropy to be like this is world entropy plus ambiguity terms, where A and B coefficient could be anything. Any A and B coefficient, this forms, if SW obeys the first law, this form will also obey the first law. So let me explain what are these thetas and k x sigmas are. So this is the event horizon, which is, you can think of a codimension 1 surface, a 3-dimensional surface, let's say in a 4-dimensional world. The cross section of the event horizon is a codimension 2 surface, that means a 2-dimensional cross section like theta and phi, a sphere for Schwarzschild black hole. So therefore, I can define two null normals, one along the event horizon and one going into it. So I can define an expansion along the congruence and I can define an expansion along the direction of LA. So there are two expansions and correspondingly there are two types of shears. So the ambiguity terms comes out to be nicely packaged into this structure. This you can easily write it down by this manipulation. Note that if it is a stationary black hole, the event horizon area does not change with time. Of course, as it's a general relativity talk, upward direction is always time. So therefore, this theta k and sigma k's are 0. So this ambiguity term identically vanishes for stationary black hole, and therefore SW becomes the black hole entropy for stationary case. In fact, if you use, interestingly, look at the Onsteiger theory for non-equilibrium state entropy, in some sense you can think of these as non-equilibrium terms, even and odd velocity terms added to the black hole entropy, and one can pursue interesting analogy with the Onsteiger theory, which is something which we are being looking for. So the point to be noted is that this coefficient A and B cannot be determined by first law. So what remember, the change of the black hole entropy now sensitive to what are these values of A and B. So you ask this question, I want to impose second law on this black hole entropy and I want to determine A and B from second law. Of course, you have only one equation, which is the second law, increased equation, and you want to determine two coefficients. Fortunately, you can do it because linearized order, the thetas and sigmas don't match. They independently give you two equations which allows you to determine A and B. So I'll not show you the calculations, but before doing that, let me just take a detour. Okay. So this is a topic which is being recently, so forget everything about black hole. Now there is another topic which is recently being formulated and is added a lot of motivated by ADS-CFT, which is called the holographic entanglement entropy conjecture. Here the idea is that suppose you live in ADS world. Okay, suppose it will be great if you have lived in ADS world, but unfortunately it shows that God has some problem. That supersymmetry in ADS is not coming out. These are all to tease Paddy. Okay, so then you have a wall. The ADS, there is a time-like wall at infinity. Okay. On that wall, on cross section of the wall, there is a quantum field theory. It is believed that quantum field theory captures the quantum gravity or say classical gravity in some supergravity limit of the bulk. So the 4 plus, say you are in 5-dimensional world, then your wall is 4-dimensional. That 4-dimensional world has a quantum field theory which tells you the property of the 5-dimensional general relativity. That's the idea. Of course, there are proofs and there are not really proofs, there are a lot of calculations which says that this is presumably true, probably true. So the idea, one of the interesting ideas is that quantum field theory will have entanglement entropy. It's one of the main non-local observable of the quantum field theory, which is very important in various condensed matter and other systems. So you take a portion of that wall. So this, only for this plot, time is not in this direction. So this is a cross section of the time-like wall of the ADS world. You can take a portion of that position and you can say what is the entanglement entropy of this region if I trace over degrees of freedom outside. Of course, this is a complicated calculation. Leading order is proportional to the area. There will be corrections and blah, blah, blah. And a lot of calculations like Shankia did in quantum field theory, many various states, what are the corrections of this, coherent state, what will be the correction. But the question is, can you calculate this entanglement entropy without doing all this correction, just by in terms of bulk observable. And the plausible answer is given by these two gentlemen. The idea is that you construct what is called the minimal surface into the bulk. That is a surface which anchors at the boundary and has the minimum area. The area of the surface divided by 4 will be the entanglement entropy of this region. And this is actually quite interesting because it's telling you the quantum field theory result will be given by a bulk observable. And it's in GR, of course, that's why I said it's a solution. The bulk is a solution of the Einstein's equation. You see that obviously you see the similarity with Hawking-Bekenstein formula. Of course, I have hidden all the H bar, I've just put in the G. But of course, it has a priori nothing to do with black holes. It may not have anywhere a black hole in the way, it's a pure radius result. What is interesting is that when the bulk is a solution of higher curvature gravity, there are several people who have generalized this formula. Okay. So, what is the generalization of this formula? So, let's take the bulk to be a solution of this and assume that it has a ADS solution. In fact, it indeed has a ADS solution. So, this is the most general second order theory you can write. Okay. So, now your bulk is a solution of this theory instead of general relativity. Boundary is again time-like, so you can construct again null normals of the cross section of the boundary. Remember, this boundary is now time-like, so the boundary is inside that light cone, unlike the gravitational black hole case where boundary, the event horizon is null. And then these people have proven that the holographic entanglement entropy can be written into this form. Note that apparent similarity with the black hole entropy with the ambiguities. But here, what is important thing is that P and Q are determined. There is no ambiguity in this calculation. It comes from the ADS CFT, basically the semi-classical limit of the ADS CFT, equating an Euclidean partition function and all those things at the boundary with the path integral of okay, I'm not going into those details how this thing is calculated. But at the end of the day, the formula gives you of this form where P and Q depends on alpha, beta, and gamma. Again, let me emphasize, this is calculated. So if you believe in that calculation, this is pakka, this is fixed. That P and Q, there is no room for anything other than adding some questions like if you add total derivative terms, what will happen? There are some issues with the regularizations of conical defects, but if you ignore them. Again, that SW is a world-like piece. It has nothing to do with black holes, again. So given a Lagrangian, if black holes, so these are the binomial of this cross sections, okay? So, consider now you have a black hole in ADS, okay, which is a solution of this higher derivative theory. So the black hole horizon is a null surface where the black hole entropy is given by this formula. A and B are so-called ambiguity coefficient. Look at the holographic entanglement entropy calculation of this ADS boundary. That is given by this formula where P and Q coefficients are known. How do I calculate A and B? I say that I'll appeal to the second law and I'll determine what values of A and B will obey the second law, the black hole entropy will obey the second law. And then what is the result we find is that if such a situation exists for a black hole in ADS, we find A and B is exactly equal to the P and Q. If we enforce second law here, it picks up exactly what is the value of holographic entanglement entropy gives you by a holographic calculations. So let me tell you how the calculation is being done. Of course, I'll not show you the full result. So suppose you like entropy to be an integral of a local quantity evaluated at the horizon. You change the entropy and this comes to the, this is the change. Note that if rho is 1, you go back to the Hawking-Bekenstein entropy. Put rho equal to 1 here, you get the expansion. So this is like nothing but an area change in case of general relativity. So you define something you call the expansion, generalized expansion. So in general relativity, the generalized expansion is nothing but change in area per unit area. In case of higher derivative theory of gravity, this is change in entropy per unit entropy. You can always check this, all this result by putting rho equal to 1. Okay. And then you calculate what is the first derivative of expansion. This is like deriving what you could say a thermodynamic Raychaudhuri equation. Like Raychaudhuri equation determines how the first derivative of the area changes. Here you are calculating how the first derivative of this generalized expansion has changed. So use all your field equation and blah, 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 non-energy conditions as expected. So you get explicitly some second order terms, which you can throw away. Second order means like, for example, expansion into shear or shear square. You say that these are small, I am ignoring it. you get some explicit terms which could be first order. These are your offending term. And then what you do is that you set the linear part of this term to 0. You get two equations because thetas and sigmas don't match, and those two equations gives you the values of A and B, and you get an equation d theta dt is equal to minus TAB Ka Kb up to second order term, which is exactly like a Raychaudhuri equation. If you remember Raychaudhuri equation, if you ignore those terms, you get d theta d lambda equal to minus TAB Ka Kb. So we appeal that same equation I should get when I replace theta by capital theta. And once you do that, you get these values of A and B, which exactly matches with P and Q. Here's the result. So if you have this full theory, so I've written this theory in a different way. I've added a gamma into Gauss-Bonnet just because the calculations is easier if you do it. And it turns out you can obtain this formula for rho, which will obey the second law up to linearized perturbation. And not only that, is this for example, this half beta, this term exactly matches with the corresponding holographic entanglement entropy if this black hole would have been in the ADS spacetime, ADS boundary condition. Note that our calculation is completely local. It has nothing to do with whether it is ADS or not. It is indeed itself is a proof of second law for some entropy. What makes it more interesting is that if this black hole is in ADS, then this matches with the holographic entanglement calculations done in the ADS, which has nothing to do with black holes. Of course, you can ask what will happen if I go to the higher order, what are the signs of these higher order terms. Note that in general relativity, all these are negative. That gives you the negative definiteness of this quantity and therefore leads to the second order, the so-called full area theorem. So you need to calculate this higher order term. It's computationally difficult to do it for a general theory. So we did it for Gauss-Bonnet where it is easier to do, okay. And there is a Vaidya-like solution, then you can ignore the shear, okay, because Vaidya is a spherically symmetric solution, although it's a time-dependent solution. It turns out it is of this form, okay. And then you can use the argument that the second law, for example, if there is a shell where TAB is 0, then outside the shell, after the shell has entered into the black hole, then everything is governed by the sign of this term. And you can evaluate on this zeta and put a condition that zeta must be greater than positive so that it has the right sign. And I get the second law up to second order. And that gives, but once you put it there, this contest, for example, in general relativity, it just tells you some d minus 2 is greater than 0, which is obviously true. But once you have higher curvature corrections, it tells you a combination of alphas and betas and puts a constraint. So the least interesting is the asymptotically flat case where the constraint simply says that there is a black hole. Okay? But if you go and do it for black holes in ADS, you get constraints on the higher curvature couplings, which is some normalized by cosmological constant, which is earlier exactly obtained from holographic consideration. So in holographic theory also, there are several consistency calculation I can tell you in later, which tells you that this Gauss-Bonnet coefficient cannot have arbitrary value. It must have a upper limit. After that, there will be some instabilities of the holographic fluid. And our calculations for second law exactly produce these numbers. Note that these are dimensionless numbers because I'm normalized alpha with the cosmological constant. So in Gauss-Bonnet theory, there are several types of horizon because it's in ADS, you can have hyperbolic horizon. For them, turns out for some reason, ADS safety calculations can be easily done. They have a constraints and exactly our second law gives you the same constraint. So there is why it is so can be explained, but the idea is that there's some sense, the holographic principle, the consistency of the holographic theory in ADS knows about the consistency of the black hole mechanics in the bulk. And that makes the whole calculations very interesting. This suggests a relationship between the consistency of holographic theories and black hole thermodynamics, which is, okay, it reinforces your belief in some form of holography, which is not necessarily string theory, because holography is a much bigger idea. String theory is just one, I would say, aspect of one realization of the holographic principle. That is the way I would put up. So this is the summary. The naive application of Wald formula does not give you correct expression of entropy. You need to have ambiguity terms, and this ambiguity term makes higher curvature theories, these corrections matches exactly with holographic entanglement theory. Somehow the holographic principle already contains the validity of the basic laws of black hole mechanics, then there are consistency conditions you can define or from the second law, which also matches with the consistency conditions of holographic theories. There are better, we definitely need better ways of understanding this result. For example, one need to write down the full variation of the entropy, say in Gauss-Bonnet, without assuming like a Vaidya or shearless condition. One need the full calculations, and it seems the full calculations also gives you the same result. Okay, so I'll not flashing it. This will hopefully come very soon in the archive. There are interesting results that Gauss-Bonnet gravity itself could have problem. Okay, Einstein was because of this Kamano and all those guys. Those understanding those in terms of this second law is important. So I point you one quotation by an interesting guy called Eddington, which all of you show. It says that whatever happens, if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing but for it but to collapse at deepest humiliation. So you should, on that, so you should take our bound seriously. Thank you.
So we have time for a couple of questions.
So if I understood correctly, the wall derivation has ambiguities, which you have now resolved. Are those ambiguities fundamental to Wald's approach, or is there some way to go back and start over knowing the answer, but apply Wald's techniques and nonetheless obtain the correction terms as well?
So I do not know what exactly you mean by fundamental, but as I can understand that those ambiguities are there in Wald's theory, because it's simply reason. For example, they are calculating, say, conserved current. You can always add another arbitrary conserved current to it. So those ambiguities arise like that, or you can add a total derivative to the Lagrangian. Wald's calculations don't change it. Now, what is an interesting question will be that take this form of the entropy. Okay, ask, is there a nice general prescription coming from the Lagrangian which will give you this particular expression of the entropy? It's an interesting question. At this moment, I don't have an answer to this question.
That was the question.
You can say that it won't come from the symplectic structure.
It won't come from the symplectic structure. One possibility could be just, you ask, is there a total derivative which you can add to the Lagrangian? This is exactly we are pursuing, which will give you this correction. But there is a problem. You have to ensure that there is no correction for general relativity. So that's a complicated thing. Yeah.
First a comment and then a comment like question, not a no, you were looking for that. Could we have some universal statement of thermodynamics, that second law of thermodynamics for higher order theories, that could it be proportional to area? And it turns out it is not proportional to area. However, there is one universality is there, that in pure Lovelock theories, it's always proportional to the square of the horizon.
Yes, exactly. I know.
Horizon radius. So, or translating in terms of the area, it is the nth root of the area.
Nth root of the n is the Lovelock.
N is Lovelock. Second thing was this your the Gauss-Bonnet theory has a ADS solution. Not only that, pure Lovelock
Also
has only ADS solution. It doesn't have a DS solution. So that for the lambda has to be negative for the even n, and it is only the odd n which admits both positive and negative lambda.
So that's why it makes it interesting to understand what happens to pure Lovelock, this kind of calculations is definitely true.
Okay, so if we have no further questions, let's thank all the speakers for this first session.
Okay, so we have a group photograph session now. So please join us outside. It will probably be in the Kund. And then we'll meet back after coffee at 11.
Thank you both.